next topic in our Limits and Introduction to Derivatives chapter is continuity. And we've used continuity a few times already, but we haven't really discussed the conditions that are required in order for a function to be called continuous. So let's take a look. A function f is said to be continuous at x equals c, meaning some value of x, given that the following conditions are met. F of c is defined. Obviously, if it's not defined, that means we either have a whole or an asymptote. Which would make the function discontinuous. Or it's simply outside of the domain of the function. The limit as x approaches c of f of x must exist. Meaning, something where we approach one value from one side and a different value from the other, even if f of c is defined, well, we'd have no limit at that point, which would give us a jump discontinuity. And then the limit as x approaches c of f of x must equal f of c. So the case in which it isn't would look something like this, where we have a hole here. The limit exists because we're approaching the same value from both sides, but the actual function is defined by a separate point here. Pretty unlikely, but it does occasionally happen. So let's take a look at a couple of examples here. The first example, show that the function is continuous at the given point. F of x is negative 3x cubed minus 2x squared plus 19x minus 5. And we're doing this at x equals 0. So this is really straightforward. You should immediately recognize that this function is continuous. But if we just do the f of 0 here, we're going to get negative 3 0 cubed minus 2 0 squared plus 19 times 0 minus 5. And we're going to get negative 5. Now, because we have no discontinuity here, no obvious discontinuity, no hole, no asymptote, no break in the domain, we also know that the limit as x approaches 0 is also going to be negative 5. So we see that they both exist and that they are equal, and thus this function is continuous. So as a good general rule, all polynomial functions are going to be continuous at all points. Rational functions may have a break in the domain, but polynomial functions, as a general rule, there's not really going to be a break in the domain at any point. Where this gets a little bit more interesting is when we get into a piecewise defined function. And what we have here is we have f of x is 2x plus 3 at x is greater than 1, and then 5 at x is less than or equal to 1. And I want to know that it's continuous at x is equal to 1. So the first thing we're going to do is we're just going to do the f of 1, which falls into this part of our domain less than or equal to 1. So we know that at that point, our f of 1 is going to be 5. Now the limit here gets a little bit interesting, because what we have here is we have the bottom part of the function basically being a left-hand limit, because that is where the function is going to be defined to all values less than 1. And we're going to take the right-hand limit here. And if those two limits are equal, then we'll have our limit. So we know that the limit as x approaches 1 from the right-hand side is going to be using this function. So we're going to use 2x plus 3. And we're just going to fill in 1 here. We're going to do 2 times 1 plus 3, and we do get 5. We also know that the limit as x approaches 1 from the left-hand side of 5, well, it's just 5. It's a horizontal line. So we then know that since these two are equal, that the limit as x approaches 1 of f of x is in fact 5, which is also equal to the f of 1. So this function is also continuous. So in the case of a piecewise defined function, we do have that change in the domain, and we have two separate pieces of the function that we have to verify from the left side and the right side.